pleased to have Raul and we'll talk about temporal things, right?
Yes.
Right.
Yeah.
Yeah, please.
Thank you for being here. So this presentation is based on a presentation by Anna Silva, which is one of the co-authors. That was 25 minutes, I think, presentation given for an event that was part of ICOP. And I guess that most of you are in some way familiar with what I mean by Menger, right? Menger theorem is a very classical one. But I guess that I would take the chance to say that most of you are actually not very familiar with temporal graphs. So maybe I will start doing some kind of explanation about very basic things about temporal graphs, and then talk about Menger theorem for temporal graphs. Okay. So starting with some basic definitions. What is a temporal graph? I mean, there are many ways and many names for this, but the definition that I'm going to be working with most is this one. Okay, it's just a pair, G and lambda, where G is a simple graph, in this case undirected, and for each edge I'm going to assign a set of integers, a set of integers, okay? And those subsets of integers are the times in which I can use those edges, okay? And the maximum value, the lifetime of my temporal graph is the maximum time in which an edge is active. So here I am assuming that edges are active at some times, but the vertices, they are always active. Okay, so in this case, the lifetime of this graph is 3. And of course, I can talk about temporal vertices and temporal edges, right? A pair xi, where I take just a vertex of the graph and a value in which it is active, I call this a temporal vertex. And similarly, I can talk about temporal edges by just talking about an edge of the graph and a value in which it is active. Okay? And just an example, let's try to understand a little bit about temporal paths and temporal walks. Okay? So the naturally, I guess that you can translate it very well from the realm of the undirected graph to temporal graph by just saying that I want now paths and walks that respect the flow of time. Okay, so okay, so in this case, for instance, this is a temporal path from S to T, right? 1 and 2. But I don't have to ask for the path to be strictly increasing. So this is like a teleportation in which I use a time for and a time for. This is also okay for me. Okay, but now if I look at temporal things, there are many ways that I can talk about the meaning of shortest path. Right? For instance, I can talk about shortest length, in which I want to use the least number of edges to go from S to T. So this is a path from S to T with shortest length in this graph. I can also talk about earlier arrival time. If my goal now is to get to my destination as soon as possible, independently of how many edges, how many connections I have to take. And I can also talk about shortest waiting period. It means that I don't want to be stuck in a vertex waiting for my next connection for too long. So in this case, this path here using 4 and 4 is the best one if this is the metric that I want to optimize.
Do you not have to wait 4 in the start vertex?
No, but I mean,
you don't
if
care
I don't care about this. Yeah, I want to arrival waiting in the middle vertices. But you're right, I can also define like this, consider this. So yeah, you're right, this might not be the best example ever. And okay, all these, they are solvable in polynomial type, which is nice, which means that the notion of connectivity translates well when you go from normal graph to temporal graph. But if you go a little bit more, then things can be starting getting a lot complicated with things that are considered to be simple in the normal cases. For instance, if I want to talk about components, right? Components in the classical sense. I can talk about components by defining relations between vertices. For instance, I define the relation P of UV if there exists a path from U to V in my undirected graph T. Okay? So of course this relation is symmetric because the graph is undirected, so if I go from U to V, I can go from V to U. And it is also transitive, right? Because it is undirected. So if I go from U to V, and I can go from V to W, then I can also go from U to W, right? So I can define a component based on this. I just define a component to be a maximal set of vertices, such that I have paths between every pair of vertices that are inside of the component, right? These define equivalent classes of the set of graph of the set of vertices of my graph. And it's very classical results that when it doesn't matter whether you are undirected or undirected, you can find all the components of your graph in polynomial time. But then how do we translate this to the temporal setting, right? We can try a very natural translation and say now T of UV to define whether there is a path, a temporal path from U to V. And here I say U and V are vertices, not temporal vertices. So I'm saying I want to get from U to V, leaving at any time from U, and get to V at any time. I don't care. Yeah. And then I can try to define temporal components as a maximum subset of vertices, such that for any two of them, I can find paths, temporal paths. But this is not symmetric, right? Because of course it's not symmetric because you can go from 1 to 2. Here is a clear example which is not symmetric. Like in the directed case, it is also not naturally symmetric. You can force symmetry if you define the relation in a way that I need to have path from U to V and path from V to U, but then it doesn't help a lot because this relationship is also not transitive. Right? I just need to look at the path from the right to left, and I don't have transitivity. And it turns out that these are easy examples, but it turns out that I tried doing this for a while, right? And it's hard actually to come up with a relationship that defines good components for temporal graph. This is actually a kind of big subject of research right now. People try to define what they think should be temporal components, and I think even deciding for some kind of definition for components, even deciding whether your graph has a component, a temporal component of size at least k, I think that is already hard. I can be complete. Okay. So we think that paths adapt well, kind of well, but components go kind of bad. So we can ask this question now: what are the natural adaptations that we can translate, like go from graph theory to the temporal setting, right? And of course, if we are asking this question about adaptations, we can also ask whether there are some easy results, powerful results, good results, structural algorithmic, that we can translate from graph theory to temporal graphs. Okay. And here I'm going to talk about the Menger theorem for temporal graphs, right? I'm going to, because there is not only one way to define the Menger property when you are in the temporal setting. So we're going to look at them and see what's easy, what works well, what doesn't work well, and stuff like this. So we're going to see what kinds of versions of Menger theorem hold, and what are the complexity of the related problems, right? Because maybe we want to find the path, so we want to find some separator. Okay, so just a word about temporal models. As I said in the beginning, I can define temporal models in which the vertices they are permanent and in which the vertices are not permanent. And there is a difference between those models. And also I can define whether my edge has a delay or whether it's an instantaneous movement. A delay, it means that I leave maybe at some time 2, but I only get at my destination at some time 4, maybe. Or I have instantaneous movement in which I leave at time 2 and I get there at time 2. Also, I can define whether I accept or not non-strict walks, which means that I can use 2 edges at the same time or not. And of course, I can consider whether I have my temporal edges being directed or undirected. Okay. And also, I think it's important to notice that if I have as input a temporal graph G with an assignment of time lambdas, what is the size of the input? Right? The size of the input is going to be based on the number of vertices of my base graph and the lifetime. They are both relevant.
Yeah, so just to come back to this, the function you always assign a finite set to
Yes.
every edge.
Yeah,
Sorry.
I think there are models that deal with infinite sets and even with real sets, but I hear is integers and finite.
Okay.
When you say the paths are like non-strict, isn't it same as saying instantaneous?
No. Actually, maybe you're right. I never thought about this. I guess no, but I'm not really sure. I need to think a little bit about this.
So non-strict means that two edges, but that appear at different time, can be used to like again. Is that what?
Yes, yes. So non-strict means that I can use this.
Same number, right? Or
Okay.
If this is not a strict temporal path.
Okay. So this temporal model appears usually like a telephone network, like
Yes,
something
yes.
like this, right?
Stuff like this, network communications and flight paths. Actually, the problem that we're going to look at Menger later is important for flight paths. I will talk about it later. And okay, so about input size, there is a weird thing that can happen, is that some problems they can remain hard even when your base graph has a small amount of vertices. Right. So, I mean, each snapshot at time I has constant size. By a snapshot, I mean you look at the graph at some time I and you take a picture of whatever is active on it. And if each snapshot has small size, has constant size, even so, we can still have hard problems. Okay. So, to simplify things, here we are going to be always considering that the vertices are permanent, that the edges are instantaneous, and unless stated otherwise, the base graph will always be undirected, and is not mentioned here, but I will also allow non-strict paths and walks. Okay?
And could you remind the instantaneous?
Instantaneous is that the edges have no delay, because I can define edges in two ways. I can define them. I mean, I can have, instead of just one number for the edge, I can have two numbers, but not like many two activity times. I mean by this that I leave this guy at time 2, but I only arrive on the other one at time 4.
So that's
This is
not
instantaneous.
Right.
Instantaneous I leave at time 2 and I get there at time 2. Okay? Alright. So, to start, what are disjoint paths and separators? Right? To talk about the Menger theorem in the classical sense. So for disjoint paths, I will always be saying that paths from S to T, they are disjoint if they are internally vertex disjoint. Okay? So for instance, if I take these three paths, the blue, the red, and the green from S to T, they do not share any kind of vertices. And a subset S is a separator, ST separator, if every path from S to T has to intersect S. Okay? And of course, you can think about the associated problems of finding paths and finding separators. This part, the problem of finding the ST path is a maximization problem, and the problem of finding the separator is a minimization problem, because you want to find the smallest one you can get. And Menger theorem, which is a very classical result about connectivities on classical graphs, just says that the maximum number of disjoint ST paths in a graph G is equal to the minimum size of an ST separator. It is a very old result from 1927. This also works for directed graphs. But what about temporal graphs, right? Okay, first I want to take a note, a moment, to study a little bit the difference about temporal walks and temporal paths, because I mean, most of the time people don't actually make the difference when you are on normal static graphs, but on the temporal setting there is a difference. For instance, if I take this graph, I mean by this little notation here, I mean that this edge is active from an interval from 1 to some n. It's active at time, every time between 1 and n. So naturally I can take an ST path like this. I can go from S at time 1 to V at time 1, and then in V I wait, and I wait, and I wait until I get to V at time 5, and I take the edge at time 5. I can do this. This is a path. Okay, this is not a walk, this is a path. A walk is when, what I mean by this is that a path is allowed to wait in a vertex, right? But a walk would be something like this. For instance, I take this at time I, and 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 this at time I again. This forms a walk because I left V at some point and then I came back for it. Okay? And there is a difference here in this example because, I mean, clearly every single path that I take from S to T has to cross V, right? So I cannot take two disjoint temporal paths from S to T. But if I want them to be temporal disjoint, then I can find many walks, right? Because each walk like this uses V at time I, right? And I can take like any temporally disjoint walks. Okay. So how do we add then the time setting to the Menger thing? We can think about vertex disjoint paths, and we can think of a separator in the way that we want to delete vertices from our graph. And by deleting vertex, I mean delete every occurrence of that vertex at every time. I can think of temporal vertex disjoint paths, and I can think of temporal vertex separator. Right now I want to find the vertex. They can share a vertex, they cannot just share a vertex at the same time. And I don't want to delete everyone. I want to delete now vertex at specific times. And also I can think whether I'm talking about disjoint walks or disjoint paths. So there is a lot of stuff that we can consider for the Menger thing. And also, each one of these kinds of definition, we will have some kind of complexity of associated problem, which we can analyze the complexity. Okay, so as mentioned before, now I'm going to talk about the Menger setting in which I will consider temporal paths and vertex disjoint. Okay, so I will say now that a set of temporal ST paths is disjoint if they are internally vertex disjoint. Okay, I'm not changing what the meaning of disjointness here. And I say that a set F is a separator, and now here S is a set of vertices if it blocks every temporal path. So the only thing that I'm adding here is that instead of looking at paths, I'm looking at temporal paths. Okay. Again, the first one is a maximization problem, the second one is a minimization problem. So we may think about what about Menger between those two values. And the Menger property between those two values is whether we want to see if the maximum number of disjoint temporal paths is equal to the minimum size of a temporal separator. Okay. Unfortunately, for this setting, it doesn't hold. Right? This is an example in which it doesn't hold, because here I do not have two disjoint temporal ST paths. This is a classical example. I forgot the author, unfortunately. So, if I want to construct two disjoint temporal paths, I have no choice from S. I have to take both edges because it's degree S2. Right? So I stop. I take this one to be the red, this one to be the blue. But then, since I use this guy at time 5, it means that the only option that I have for my red path is go here at time 6. So you can see that I block the blue path. So I cannot find both without sharing a vertex. Okay. This means that the size of a maximum collection of disjoint temporal ST paths is 1. But what if I want to separate, to break all the paths from S to T? Right? Then in this case, the minimum size of a temporal ST separator here is 2. Right? Why? Because if I remove only X, I can go from S to T taking this path. If I remove only Y, I can go from S to T taking this other path. If I remove only U, I can go from S to T taking this path. So although I cannot construct two disjoint paths, I need two vertices to separate all paths. So it means that the Menger theorem doesn't hold in this setting. But then I can talk about in what cases does Menger theorem hold. For instance,
Sorry, could you go back to the previous slide? So if the edge between Y and T had, for example, 5, it was also active at 5, then we have two vertex disjoint temporal stiffness.
from Y and T, if it's at time 5,
Yeah.
I don't think at time 5 it solves this.
Then you can,
But
you have 5, 6, 7.
yeah,
But you cannot go 5, 6, 5.
yeah, because here is not temporal disjoint. I don't want any temporal paths
But
to
you
share the
can-
same vertex.
But you can go from S to X to Y to T, and from Y to T you can use also like
Yeah, but-
time 5.
but-
Maybe I missed the
Oh yeah,
definition
but
of-
the thing is, if you want a true path,
Yes.
you need the second one.
So it's
Yeah, so I mean, so I want, so if I put two numbers on the edge between Y and T.
and so it doesn't solve anything in this
Mhm.
case because what I want here is that the paths cannot share the same vertex. So if a graph path uses Y, I
Right,
cannot
so
use
no
Y,
one else,
can use
okay.
Y at any
So it's
any other
not
time.
Like, it's not temporal disjoint, but really
No,
vertex disjoint.
Vertex is
Okay.
Mm-hmm.
But then, okay, I can try to analyze what are the graphs for which this setting of the temporal of the Menger thing works. Okay, I call a graph Mengerian if the equality between those two values, the maximum number of temporal paths and the minimum size of the vertex separator, is always there is always the equality, which means that since I'm only talking of G, it means that the equality should hold for every choice that I make of S and T, and for every possible time assignment that I give for the edges of my graph. Okay. And there is this result from Kempe, Kleinberg and Kumar from Stock that says that if every edge of my graph has exactly one time in which it is active, then the graph is Mengerian if and only if it doesn't contain a subdivision of this graph, which is called a gem. Okay, so there is a characterization of when Menger property holds in this setting when the edges have only one time assignment. But we can do a little bit better than this. So these are two co-authors of this paper that I'm going to talk about, and they extend it by saying that a graph G is Mengerian if and only if it doesn't have any of these graphs as an M subdivision. So M subdivision is the M before multiple. It's not a number. It just says that if my graph can have multiple edges, and a subdivision of a multiple edge is I subdivide everyone.
By the exact same number? So,
M is not a number.
oh,
It's just to say that I can do subdivision of multiple parallel edges. I have to do if I have a set of parallel edges,
yeah.
so it's like this.
Yeah, the picture would be great.
Yeah. Yeah. I guess it would.
So G will always be a simple graph?
Huh?
G will always be a simple graph?
Not in this case. I
Okay.
guess not in this case.
Not in this.
Yeah. So I can start with this. So an n subdivision of this would go.
Oh.
Right.
So I guess a figure would be good here. Okay. Oh yeah, and they can be recognized in polynomial time. Okay. Okay.
So if that means like if my graph is simple, the second and third case is
Sorry?
if my graph is simple, the second and third
Yeah.
I can
Okay.
ignore them.
Previous one.
But this doesn't require lambda to have only
No,
one.
exactly. This is why this is strong.
Okay.
This doesn't. You don't need any kind of property of the edges here.
Mhm.
Only that the graph doesn't have these as M subdivisions.
Okay, I have one more question about the end subdivision. Can you subdivide the multiple edges normally? Like, could you subdivide, say, one of the two edges?
And not the,
Separately?
no.
You have to.
You have to do this.
Okay.
Oh.
So what difference does the parallel edges make if the edges can have multiple times associated with them?
Sorry?
So we're not saying that each edge has only one time association.
No, it can have multiple times.
But, okay, but that's not what the parallel edge. Is that what the parallel edges represent, or is that something?
No. This is a thing that happens on your on your. Sorry.
Sorry.
Yeah, I mean, if you have a parallel edges, you can just merge them.
So are we still talking about the vertex disjoint case or the edge
Yeah.
disjoint?
Yes, here is for the vertex disjoint case. So this seems like I have a vector to them. So this is for the vertex disjoint cases in temporal paths, right? And this is a characterization of which kinds of graphs, temporal graphs, satisfy the Menger property on this scenario.
So, but what is the difference between you having two parallel edges, one with time 2 and one with time 4, or just having
Yeah.
one edge?
Yeah.
with
I
time
think
2
I
and
think
4?
you were right. Maybe I'm mistaken here, and I think you should be able to subdivide just one.
Mhm.
Is it so? So is it the parallel edges represent the multiplicity of the number of times? as well?
No. So this is a thing that happens on your graph, on your undirected graph. This,
Yeah.
right? And then you can have different times for this.
Yeah.
But I guess that your question makes a lot of sense. What is the difference in between only have this once, right? But then I guess it's because if you want vertex disjoints, that's a good question actually.
No,
I'm
I'd
not
like
really in
this-
favor.
Yeah,
Also,
like
so-
another-
sorry for all the technical questions. If you subdivide an edge, what happens to the times on the?
So this is not, the subdivision doesn't take in consideration the times.
Okay.
Yes.
Okay.
So I mean, I'm saying that my graph doesn't have, my static graph G, which I have no times, cannot have any of these guys
Mhm.
as an M subdivision.
Okay.
And then if this is true, whatever is the assignment that I give of timing for the edges, I will have that the Menger property holds on the temporal graph that I generate like this.
Oh, okay. So if you have this diamond graph or whatever it was called,
Yeah.
gem. Sorry. So is it a bad example no matter how I choose?
That's a question,
times?
actually. If there is a gem, I give you a gem. Can you give me, maybe I give you this or this, any of these three. Can you give me an assignment of times for which Menger holds?
Yeah.
Okay.
So for parallel edges, maybe the situation may make differences when S is one end and the T is the other end. Then you can use two.
Yes, you're right.
Two paths
Yes, so that's
instead of
one
edge,
example.
right?
That's one example where what make a difference, because now if your path only want to be internally disjoint, then every edge that you have between S and T forms a path.
So I must, this is maybe the same question as you just answered, but suppose, I mean, this is a bit like I fix a graph G and then I'm asking when this Menger theorem holds for any time assignment, right?
Yeah.
But we can ask some different question, which is given a graph G, what are the time assignments for which Menger theorem true, right? Do you also
Okay.
consider something like this?
You can, but I don't know any kind of result in this direction, but I guess it's also a meaningful question. But yeah, you can. I mean, what are the structures that I need to have on graph G such that I can give a good assignment, an assignment that makes sense, and I have Menger. Yeah. Okay, so now I'm going to talk about temporal disjoint walks. And now the difference is that I want the walks to be temporally disjoint. So they can share a vertex, they cannot share a vertex at the same time. So this is the same graph from the previous example. And you can see that now I can construct two paths, two temporal paths that do not share a vertex at the same time. The blue one and the red one, they are sharing the vertex U, but U is used by blue on time 2 and 3, and this is by random time 5 and 6. Okay, 2. And the size of the separator is the same thing. I can block all paths from S to T by taking x at time 1 and u at time 5. So now my separator is a subset of temporal vertices.
So
If the 3 and the 7 were switched, would it count as using u at the same time because the 1, 2, 7 path is waiting at you while the other one's passing through, or does that not matter?
If they intersect in u at any time, even if one is waiting and the other is moving, it still counts as an intersection.
so for this specific, this type of a case, I kind of imagine that I have a time tau copies of the graph, and each time t, then I only activate the edges which are active at the time, and then ask maybe in some sense we try to reduce that problem into the standard setup of Menger.
Yes, you could try to do this, but I'm not really
This
sure
doesn't
that
work.
it will work. There's a lot of information that you are losing there, because if you are looking only at pictures, you are not really sure about how the weighting works. But there is a way to kind of see temporal graph as an undirected graph, right? In which you draw the vertices like this. Like you have this is a vertex V, and then I have times 1 to n here,
Yeah.
right? And then I add this is u, and I add an arc like this,
Yeah.
Right.
representing time. So you can do this, and this is actually very helpful if you are looking for paths or branchings inside of temporal graphs. But for Menger, I don't think it works in all the cases. Okay. Okay, and the separator. So I have here 2 walks, 2 separators. And so if I'm looking for temporal disjoint, and I'm looking for temporal separator, then Menger holds. Okay, very simple statement here. The maximum number of temporal vertex disjoint paths is equal to the minimum size of a temporal vertex separator. So when I add this little t here, I'm just abbreviating the temporal thing. And also, the path and the separator, they can be found in temporal number time.
I imagine that you use something like this to prove this.
I don't know the proof,
Uh-huh.
but I guess so.
Because somehow any path in there will be such a temporal walk like this.
Yeah. You can, yes, you can add edges from here to here. I'm not really sure. I mean, I'm not a specialist on the technicality of this proof, but
I can imagine.
yeah,
this might be
I
done
can imagine this
separately.
could work, but I don't really not telling you for sure. Okay, so we can see that if I'm talking about temporal disjoints, there is a difference between walks and paths, right? Because now, what we have seen so far, if we are talking about vertex disjoint temporal paths, but vertex separator, then Menger doesn't hold. If we are talking about temporal vertex disjoint walks and temporal vertex separator, then Menger holds. And now I'm going to mix both things, and I'm going to talk about temporal vertex disjoint paths, not walks, and I want to separate them with temporal vertices. Right, so it's a path from the top, only paths, but I want to separate them with temporal vertices. So also doesn't hold in general.
Can you reiterate what was the difference between the
Okay, so here,
temporal vertex disjoint walk and temporal vertex disjoint path? Walk and path. The difference is what?
if I have temporal vertex disjoint walks, we can share vertices but not at the same time. And temporal vertex separator, in which I want to break the paths, choosing vertices at some times.
But-
Can I ask about this again, going back to the
Yeah,
example before? So there you have the vertex separator, right?
So here I have 2
But
temporal disjoint
actually-
walks.
Yeah, if you take a temporal vertex separator, then you would need those 4 things.
No,
right?
you need only 2. You take x at time 1 and u at time 5.
Ah, okay.
Ah, okay.
Hang on, but what about the path s to x, x to u, and u to t?
There is no path from x to x if I remove
Oh,
this.
yeah. Oh, sorry.
No.
Yeah.
But what about the path S U U Y
There
Y
is-
T at time? I don't know. Sorry.
You also don't have. There is only. You don't, yeah, I know it's confusing. I know. That's why it's slowly.
So
It's
if
good that you were
yeah,
asking questions.
I guess the problem was in my mind, if a path sits in a vertex, then I actually don't only need to block one time over the entire waiting period. I don't need to block the entire waiting
Yeah.
period.
Yes.
Mm-hmm.
And if I block this guy at time 1, there is no way to go from S to X. And if I block this guy at time 5, there is no way to go from S to U.
Yeah.
Okay. So here again, the same part of confusion. If I talk about vertex disjoints and vertex separator, then Menger doesn't hold. If I talk about temporal vertex disjoint and temporal vertex separator, and I'm talking about walks, then Menger holds. So the difference from the second to the third is that I'm going from walks to paths.
So you can be the same vertex again? Or you cannot be the same vertex?
I can wait, but I cannot go out of it and then come back. But then, even in this case, Menger in general doesn't work. This is an example. It's a little bit more complicated than the other one, but we're going to go through this step by step. So the goal here is that I want to show that I cannot construct 3 temporally disjoint ST paths, not walks. Okay. So if I want to construct 3, and S has only 3 temporal edges going out of it, right? So I have to use all 3. So I take all 3. I give each one of them a column. Okay. Now the red path is in X. So how can I extend the red path? I have 2 options. I can go at time 1 to U, for instance. But then if I do this, then the only option will be to go through Y, and I will clash with the blue path. Okay?
Yeah, because if you use 2, then because the blue path has to wait in
Anyway, yeah. So if I, yes. So the other option that I have for the red path is that I take it here, and I go straight here on the 2. But then if I do this, I cannot construct the green path that I had previously, right? Because the green path would have to take like the other edge and would clash on X on the waiting period. So the best thing that I can do is make as 2 paths, the red one and the blue one, which implies that the maximum number of temporary vectors joint paths here is 2. But then the minimum size of a temporal separator, in which I don't want to remove vertices, I want to remove temporal vertices, has to be 3. Okay. Why is it? It's a little bit more. Yeah. So it's a little bit tiny for sure. But suppose that I cannot remove only x2 and y1, right? Because otherwise I have this red path come through from S to T. And I cannot remove only x2 and a choice of y at time 2 or y at time 3, otherwise I can also avoid, I can also construct a path avoiding those guys like this. And the same thing holds like for the other direction. When you look at that, I'm only going to pick this guy y at 1 time and x at 2 times. But now since I'm taking both edges that are leaving S, I'm blocking both of them, right? Because I'm taking x at time 1 and x at time 2. And I'm blocking now all the edges that go from S to Y because I'm taking y at time 1. So if I take these 3 vertices, here, 3 temporal vertices, I block every path that goes from S to T. Right?
Okay, can you get one more?
Yeah, there is a little bit of analysis to show, but
So what happens if you take x's at time 1?
So we want to say like y at time 2 and x at time 1.
Can you not take them at the same time?
You can,
Okay.
but I don't
What
understand
is
what
that?
you mean.
Sorry.
This example is a little bit more complicated to see, but if you spend some time, you
So for the work, you just go from S to X and X to U and U to X, right? So you just use U as a weighting style.
you can, yeah.
Uh-huh.
So here is exactly what's going on. I go from x to y, then to u, and then here I wait because I cannot take x at time 2 because I'm picking it in this case. Right? So I wait here, and then I go on time 3 and then on time 3.
Mm.
So yeah, so if you are trying to block with temporal vertex, it's a little bit more complicated. So with a little bit of analysis, we can see that the minimum size of the separator has to be 3 temporal vertices. Right, so it's another counterexample because I can only have 2 paths, but I need 3 temporal vertices to break them all. So if I want to describe what is the Menger property in this scenario, is where I want to see to test whether the maximum number of temporal vertex disjoint paths is equal to the minimum size of a temporal vertex separator. This is not true in general, but in a surprisingly complicated result, this is like a not an easy proof at all. We can show that it actually holds. So we know that it doesn't hold for more than 2 paths because of the previous example, but it holds if you are if you have exactly 1 path. So in this particular case, is the only one that works in general for the setting of temporal disjoint paths and temporal separators. This is something that we show. And but what about the related problems? What if I want to find the paths or the separators of everything? For instance, what happens if I want to break all temporal paths with temporal vertices? I guess I will skip some parts because there are many questions in 40 minutes. I know exactly what I'm going to skip, but this is an easy part. So I want to break all paths, temporal paths, with temporal vertices. It's an easy test, intuitively. You just need to test whether your set S that you are taking intersects all temporal ST paths. Testing this is called NP-complete, but it can be done in XP time. Okay. So, as an example, these are the last 2 things I'm going to talk about, this and how to use this. Yeah.
Can you show the running time again? H to the H times M times.
Yes, H is the size
Tau.
of the separator.
Right.
And tau is the lifetime. And
So why is it XP time? FPT time.
XP time on when the size, when the input size is the tau, the lifetime,
Mm-hmm.
and the number of edges of your base graph G. So your base graph G has m edges, and the lifetime is tau. Oh, sorry, here is not XP. I mean, what I mean to say by this is, if they give me an S, then I can test if it's in separator in FPT time,
Ah, right.
but
okay.
find in a separator is XP,
Okay.
because I don't know where it is, so I have to test for any set. Sorry, this was my mistake. Okay?
So the second one is for testing whether S is temporal
Yes.
separator.
Yes. Testing whether S intersects all paths can be done in this time. But then I have to, if I want to find a separator, I have to test for everyone. That's why it goes to XP. So, as a simple example, I'm going to look at how to decide. I give you an S, a set S, and I want to decide whether it is or not an ST temporal separator. Okay, and to simplify things, I will say that every temporal vertex that appears inside of S is a copy of the same vertex of V. Okay, so I have like 3 temporal vertices in this, and I have 3 temporal vertices in S. U at time 1, I1, U at some time I2, and U at some time I3. Okay? And I want to test whether this S that I'm giving you intersects all temporal ST paths. So since I'm talking about paths, I know that every path will enter and leave S at most once, right? Because S only has U, right? And it cannot enter and leave U, otherwise it would be a walk. And since I'm taking S to contain U at these times, I also know that I cannot like get inside of S in this interval of U between the time I2 and the time I3, and leave at the interval 4 after the time I3, right? Because this implies a wait. It means here that I'm getting from S, I'm getting to U at some time here, and I'm waiting to get out at some time here. But I cannot do this wait because here it's blocked, right? I cannot have a path from S to T that crosses from an interval to the other. Okay. But then what this gives me is that I can a characterization of whether S is not a separator. What we prove is that S is not a separator if and only if there is a temporal ST path avoiding every temporal edge incident to U at the time that is not a sum interval. In this example here, I'm looking at the interval I4, and I want to test whether I can go from S to T in the temporal graph, where I delete every temporal edge that touches U at this interval, and at this interval, and at this interval. I only keep the edges meeting U at this interval, which these are okay, right? It means that what the best that I can do to find a path from S to T is get inside one guy here, and wait a little bit, and then get out. And yeah, so this is what we do. We pick an interval. There is a small number of them. The number of intervals is close to the size of the separator, right? And for each interval, I just test for connectivity, right? But this is from when the case for S only contains one copy of a vertex at different times. If S now has many copies of many vertices at different times, then it becomes a little more complicated. Okay, but this reduces the problem to the problem of testing connectivity. And this test of connectivity, this can be done in polynomial time. Okay. So from the previous slide, we know that we can test whether there is a temporal vertex separator of size 1, right? One temporal vertex in this time. And we can use this information and the Menger theorem for k equals to 1 to find two temporal disjoint vertex paths in your temporal graph, right? Because you have a way to clean up useless edges, right? First we test whether we take our temporal graph and we test whether there is a separator of size 1. If there is a separator of size 1, then we don't know. There are no two paths from S to T. So there is nothing to do, just say no. If this is not the case, we just make a copy of the temporal graph, and then we just start deleting temporal edges, right? Because we can delete it, we can pick an edge and delete, and then we test the connectivity. We test for the connectivity, right? We can do this iteratively until we remove every edge that is not necessary, not needed to construct two temporal disjoint ST paths. Right? This is what we do. For every temporal edge, we test whether we can delete it safely from the graph. At the end, what we get? We end with, if every time that we do the test, the answer is no, that we don't have a separator of size 1, it means that we removed every edge that was not necessary to construct the path that we are searching for, and it means that we end with an edge minimal temporal graph that contains exactly two vertex disjoint paths. And then with this information, we use the minimality to finally find the path that we want. It's actually not exactly trivial to find this path, even when you know that every temporal edge is part of one of the paths. Okay. So since there were many questions, I guess I will skip to the. Oh, sorry.
Okay. So in step 3, you are removing redundant edges, is it like the vertex separator should belong to? So if the vertex separator actually hits every temporal SD path, then the edges deleted in step 3 will be irrelevant. So
Yeah, this is what we want to do, right? Because every time that we remove an edge, a temporal edge, we can only reduce the connectivity of the graph.
right.
So if we start with a temporal graph and we test, and the size of the separator is not 1, it's greater than 1, then we know that we need to have at least 2 paths, right? Then we just start deleting edges while maintaining this property until we delete everything that we do not need. Yeah, at the end what we get is just one temporal graph that is minimal, edge minimal, and contains exactly 2 paths from S to T. And then we have all these properties that we know that the paths are there. We know that every edge is inside of one of these paths, then we can find the paths. So we'll go forward. Yes, it should be one thing here. One of the questions interesting is whether we can detect a separator in FPT time, actually, because we only have XT. We don't know what we can do in FPT. Now we'll skip because we are close to the time. Let's start with my questions. You can see that it was a cool reduction. And I will finish here. Yeah, so this is a big table. I can help you try to interpret this if you want, but it's just saying that the pink things is the things that we did on this work, right? The white things were results that were already known, okay? And this equality in the middle, it only says whether the Menger theorem holds or not when you are considering these scenarios. So for instance, here is I want to talk about vertex disjoint walks or paths. And vertex separator, then Menger theorem is not true. Then I want to talk about temporal disjoint walks, then Menger is true. If you are talking about temporal separators, it's a big table. So yes, I want to finish here because it has been a long time now. So hopefully it was something new and interesting for some of you.
Thank you. Any questions? Yeah.
Can you define weighted temporal graphs and if on the flow of those graphs?
Flow?
Flow.
Like flow problems.
Yeah.
So there is a version of flow problems, I think, that works for temporal walks and temporal separators. I think so. Flow there is polynomial,
So
maximum flow.
So that can you extend the whole two-person algorithm for such a weighted temporal graph?
For some cases, you can extend some of the algorithms. Yeah, but not for all. I mean, there is, I think that the case, so maybe I'm remembering correctly, but I think that the case that translates to flow is exactly temporal for temporal paths. I think. Yeah, I don't exactly remember. There is one translation, one scenario that works.
So I got some vague questions. So when I heard about your talks, what I imagined was this time copies of the same graph with the instantiation of edges in each time step. But at the same time, because of weighting, you can also connect node at time t to node at time t plus 1 because I can weight the intersections, right?
Yeah.
So if you do so, then you can, because it's a graph, you can apply the Menger's theorem and so on.
Yeah.
So now I ask myself, okay, what's the difference between what you're doing and the Menger theorem? One difference may be that you define some kind of equivalence relation, especially the first questions, equivalence relation on the vertices based on the time. And then when you count like the disjointness, your disjointness is, if you just hit one vertex in the equivalence class, you hit everything.
Yeah.
So you kind of try to say something about disjointness of these touched equivalence classes and counts. Try to connect this Menger theorem on the level of equivalence relation. So I'm wondering now, if you just take the equivalence relations, then you can take any graph and take any equivalence relation and ask exactly the same question. Maybe it's so vague, so no structure.
I kind of understand what you're saying, but
Can you get any result of that kind?
So
say?
I try working with equivalent relations for temporal graphs to define connectivity relations, like to talk about temporal components and stuff like this. But it turns out it's hard to actually find something that actually defines an equivalence relation, right? And it's also meaningful. Unless you make it like extremely arbitrary, extremely strong, you will not get an equivalence relation. So you either get something too strong, or you lose the partition effect. I don't know. I tried working with equivalence relations with no success.
Can you say what you mean by you get something too strong for the component definition?
Yeah,
Something too
it's
strong.
because as I mentioned right in the beginning, right, it's hard actually to think about what would be a good relation of path existence, like that includes time and gives you a notion of a temporal component, right? That is not too strong. I mean, you I'm not really sure how to answer your question. I mean, because I have tried playing with these kinds of things, and either you get with something that is arbitrarily strong, and is not doesn't have any kind of algorithmical meaning, is not useful.
Yeah, too restrictive.
Too restricted.
Do you mean, for example, if every vertex is only equivalent to itself?
Every vertex is what?
It's
Sorry?
only equivalent to itself.
You can maybe say this.
But you want something that particularly describes the existence of a path,
Yeah.
and also is through the existence of a path.
Yes, but then you want a temporal path, and then
Yes,
you want it
yes.
to be at the same time transitive and symmetric, and it's hard. Actually.
Can you get some like partial order or define some order that would be relevant to your problem?
I don't know. Yeah.
How about the S disjoint boson?
As disjoints.
Yeah,
Oh,
instead of vertex disjoint.
there is a. If I go right through the end.
Oh.
So there is this notion of all the temporal version of Menger theorem, in which they now want the notion of disjointness for them is no departure time. So I can share more things. I just need to be. I cannot leave the same vertex at the same time.
Okay.
So it's a little, and this is close to the edge version of Menger actually. I really don't know how close it is, but it's kind of close. I mean, there's a comment that the authors make.
You can imagine some train station with a
Yeah.
limited number of tracks. Or
Yes.
something. Okay. Any other questions? Yeah.
So-
Oh, go ahead.
Okay, maybe for this version you just mentioned, does it also make sense to maybe place a weight on the vertices to say, okay, at the same time they're allowed to be so and so many things, paths waiting in this vertex?
Yes, maybe.
Because I
guess
mean,
it
for
might-
modeling this makes total sense,
Yes.
right?
Yes, but I guess, I mean, it could make sense. I don't really know how to give a strong answer for this question. But,
So,
yeah.
so if, I guess this temporal network was, well, it's motivated by like real world examples.
Yes.
So in
No.
most cases, I think it makes sense that edges will appear like over many times over time, right?
Yeah.
And the time frame is like not small constant, but it's a very large
Very large,
constant. So under this setting, I think, so for example, every edge has, so if every edge occurs like with periodically, but every edge with different period, I guess, and if your time frame is super long, I guess there should be a like good notion of equivalent relation to define connectivity, for example. So like, but so here like first, like every edge had just one integer, like okay,
Yeah.
that kind of assumption doesn't seem. It
Yes.
seems a little bit weird,
Mhm.
considering the motivation of this model.
You're right. It's I
Right.
guess because if you have like many options and you have a guarantee that there will be different periods, then maybe yes, then maybe you can find something that works for components maybe.
Interesting. Other questions? If not, let's thank the speaker.